they want me to find the first and second derivatives. So G prime of T, product rule, we will say first times derivative of second plus derivative of first remember that'll be chain rule times derivative of inner would be 4t times original second. I think the trick to this will be trying to rewrite it so that we can get the second derivative without a lot of mess. Yes. Either way you do it, just so you do it. Yeah. Yeah. So, just so you have these two terms, it doesn't matter which term comes in front. Okay? So, if I combine that just a little bit, look at this. 2t squared minus 1 squared, 6t. I'm going to call that 8t times 3t squared. That would be 24t cubed. 2t squared minus 1. Okay. Would it be smarter to try to factor that before I take the derivative again, or just do it for two product rules? That's the big question, probably. I would probably just go straight to doing the product rule twice again. So that would be first times derivative of second plus derivative of first first times 4t times original second. And then do it product rule for that second term. First times derivative of second plus derivative of first, which would be 72 t squared times original second. This is the second derivative, and you could spend about 15 more minutes simplifying it. So I'm sure the book gave a more simplified answer than that, but the rest of it's just distributing, trying to rearrange it so that you have the simplest possible. And I don't know if that's worth our time or not, but if you understood it was just basically doing the product rule, then doing it again, and you had a bunch of terms. The rest of it's just algebra trying to get it down to the particular number.
So you wouldn't matter what they book did is factor out the GCF.
Here's a good point. On your test, when a lot of you did, I think it was, I don't know if it was product rule or quotient rule on one of them, got kind of long. Some of you actually simplified it all. And I don't know, maybe one person of everybody that simplified it got it exactly right. But everybody had theirs right when it was like this. Everybody had this right, so I counted it correct. But sometimes you did the simplify it down. Everybody had a little different, like a sign or a term was off. And I marked it, but I said, I put a box around this. I put a box around this, and I said, if you gave me that, you were fine. Or the quotient rule. If you showed me where it all came from, you just made a mistake simplifying, I didn't count off. Just show me that you understand how to. That's what I'm saying. But you understood the concept of taking a second derivative, right? Today, what we have to do is just show why we need that, and how we're going to use it. And that's going over to 4.2. Okay? So if you want to turn over to page 279, okay? I'm going to draw two increasing functions. Here's one of them. You agree those are both increasing as you move from left to right? They're both increasing. This one is increasing slowly. Concave down, right? Increasing slowly. This one's increasing quickly. Okay? So like I said, you notice this is curved downward. It's concave down, isn't it? All right? Curved downward. This one is concave up, curved upward. Okay? Think about this. What if I took different points on this first one and we looked at the derivative? Here's the derivative here, slope of the tangent, slope of the tangent, slope of the tangent. What's it doing? It's getting smaller towards zero, isn't it? So that's what we could say about that. The derivative f prime of x decreases. Oops. Derivative f prime of x decreases towards zero. What about this one? If I took different points on this one and found the derivative, slope of the tangent, slope of the tangent, slope of the tangent, that's increasing, isn't it? We would say the derivative f prime of x is an increasing function. Increasing function. For that one. So that's what I want you to get from this. If your function on a certain interval is concave down, the derivative's decreasing. If it's concave up on a certain interval, the derivative is increasing. Okay? Well, if we took the derivative of the derivative, we could find where it changes, right? Where would it change from concave down to concave up? That's going to be our big question in this section. So, now that I've sort of drawn those for you, here's where we could switch to our D2L notes. Oh, by the way, from 3.5, here were all of the different notations for second derivative that you might see. And I sort of showed you those last time. Remember f double prime, y double prime. If you want to do the dy dx for second derivative, you could do it either of those two ways. These all mean second derivative. Okay? Well, here's the question I wanted to ask them, following from those two graphs I drew. To find out if that first derivative is increasing or decreasing on an interval, take the derivative of that first derivative, which is the second derivative, f double prime. Okay? So that's going to help us tell if that first derivative is increasing or decreasing. Okay? So here's our definition. The graph of y equal f of x is concave up on an interval ab if the second derivative is positive for every x in ab. That makes sense, doesn't it? It'll be curved upward if the second derivative is greater than 0. Okay? Very good. The graph of y equal f of x is concave down on an interval if the second derivative is less than 0, if it's negative. So if you remember what we used to do, let me draw it up here. Okay? We used to worry about this in the last unit. We used to say, I'm mainly concerned if I had a function we were concerned in the last unit about where the relative max and relative min points were, right? Okay? Well, look at this. Would you agree that on this function, this interval is concave downward, curved downward? But this is concave up, isn't it? where did it switch? The second derivative is going to help me find at what point it changes from down to up. And that's going to be called the inflection point. Inflection point. Okay. So instead of finding max and min now, we want to find where it switches from curve downward to curve upward. And that's where it would change. Okay. So how do we find that? Real easy. Real easy to do. Look at this. Here's my definition for inflection point. Points of the graph where the graph changes from concave up to down or vice versa. Okay. Just like I was showing you on that graph. Points where it changes from concave up to down or vice versa. To determine the intervals on which the graph of f of x is concave up or down, here are your steps. First, find all zeros of f double prime, the second derivative, right? And any numbers for which f double prime is undefined. Okay. Just like we did, remember when we would take the first derivative, find our critical numbers and split the x-axis into those intervals, and we would say, is it increasing or decreasing, positive or negative? I'm going to do the same type thing, but this time with second derivative. Look what we're going to say. We're going to test an arbitrary value of x into the second derivative from each of those intervals we created, right, to determine the concavity. If the second derivative is positive, it'll be concave up. If you plug in that x and it's negative, that interval will be concave down. Right? Let me move it up just a little bit. If the concavity changes at some x value, it's an inflection point. So look at my picture again. I'll bring this back up in just a sec. But if I can tell numerically where this changes from down to up, right there, if I could find that point, that's my inflection point, and I could find exactly where it switches. That's going to help me in a lot of different cases. Okay? So that's what we're doing in this section. We're going to try to classify those intervals as concave up, concave down, and find any inflection points. I think the first one we should probably do, which is interesting, is 26 on 279. 26 says g of x equals x to the fourth plus 1 half x squared plus 6x plus 2. The instructions say show the graph is concave upward wherever it's defined. Well, what's the first derivative? Yes. What is the second derivative? Would you agree that I don't care what number I put in for x, that answer would always be positive, wouldn't it? If I put in 0, a negative number, or a positive for x, if I put it in there and work it out, it's always 1 or above. Like you're squaring x. So that means this function is concave up for all x. And you could prove that by graphing. It's concave up everywhere. And that's what they want you to show. But what if you set your window on? Wouldn't you rather just do this and say, hey, that could never be negative? So I know it's always negative. If you graphed it, you would see that. If you graphed your original, you would see that it's always concave up.
So it's not going to have any impact.
No, it don't. It wouldn't. Because see, let's graph it.
Well, because you're going to find 0 from the second derivative.
X to the fourth, call it out to me. X to the fourth plus 1/2 x squared. Uh-oh. Let's see. Okay, good. X to the fourth, come out of that. Is plus 1/2 x squared. Squared. I look at that. I didn't think of my plus either. Let's just not be very, let's not agree with you. Come down, insert a plus. There we go. I need to look at it. What was it? Plus 6x plus 10. If I leave that on a standard window, can I see it? Let's take our window up. Y max, how about up to 30? See that? If you kept zooming out, it never comes back down. It's always concave up. It never changes. It never comes back down. But see, what if you didn't trust yourself? What if you said, well, what if I zoomed out 1,000,000 times and it finally came back in? Well, it's not. And the way you could tell that sort of is these are all even. Well, the x is not even, but it never comes back down. Those are going to dominate, and it's going to always rise. And our derivative tells us that. So it will never switch come down. Any x you put in, it will always come down. For infinite, negative infinity. Do you see from 29 all the way to 48, they say determine where the graph is concave up and where it's concave down. Let's pick a front end. Let's see. How about 34? That's pretty good. 34 says f of x is 3x to the fourth minus 6x plus x minus x. What's the first derivative? Like that. How about the second derivative? I like that. Okay. So, if I set that second derivative to 0, that's going to tell me where my possible inflection points are. That's going to split my x-axis into intervals of concavity. So would you agree I can factor out what? What's left? Right. So if I set each factor to 0, yes. So 36x is 0, x is 0. And if x minus 1 is 0, x is 1. So look at my intervals. Negative infinity to 0. Then what? 0 to 1. And then 1 to infinity. Those two numbers split my x-axis into those three intervals, just like we did with increase and decrease, right? In the last one. Well, I want to say, what is f double prime of a number in there? I bet most of you pick negative 1. If I pick negative 1, that would be 36 plus 36, which is 72, which is positive. So what's that times 2? Up. If I put f double prime of 1/2, well, 36 times a fourth is 9, minus 36 times a half is 18. That's negative 9. Am I right? If I plug 1/2 in for the second derivative, since that's negative, it's what? And what about if I plug 2, which is inside that unit, plug 2 in to that double pipe? 72 again. Concrete up. Here's my result. Let's test it real quick. I bet you can type it into the document. 3x to the 4th. What if I just said insert 3? What else it would say? Minus 6x cubed minus 6. And then it was plus x plus x minus 8. Whoops. Almost. Look at your graph. There's root 6 again. Look at that. I'm going to go down a bit on my window. I'm going to say y min negative 3. Okay? So look at this. It was, look at our intervals again. From negative infinity to 0. Look at that. What did the concrete up? At 0, it changes slightly to concrete again for a while, doesn't it? From 0 to 1, just from 0 to 1. It's like that. Do you see that? And then from 1 to infinity, it's back up forever, isn't it? So it was up, then it was down, and our graph back that right up. And if you wanted to know where it did change, right? What if I just went to my table? And what if I entered those numbers, which were the zeros of my second group? If x is 0 in my original function, 0, negative 8 would be the inflection point. And at 1, negative 10 was the other thing. That's where they change. If I look at it again, 0, negative 8, look at that. You see that switch. It looks like it's right in between where it's rising, right? That's where it changes. And then at 1, negative 10, that's the other inflection point where it changes from down back down. Good. That's not hard. That's good. You just have to get it in your head. What people always have the most trouble with, they're still thinking max and min in this section. And we're going to be doing some of that, but mostly we're looking for inflection points. Where is it changing from this to this? Where my fingers meet, right? Sometimes not. You saw that. It might not be halfway between there. It might be closer. You never know. It's all in the calculation, right? Where it actually changes. But this procedure tells us that.
But on that, if you want to, that's really just volume all of the points that you want for inflection because it goes from negative y to positive substantially. Do you want that point also?
On this question, this is all they want.
Of course, right.
What are the intervals? What's kind of
If
This is all they asked me for. They didn't even ask me what the inflection points were. That's in the next little section of the problem. So all of these down to 48, they just want this answer. Find your possible inflection points and split your x-axis into those intervals and test. If you get a positive result from your second derivative, concrete up. If you get a negative result, concrete down. And then if you're not sure, if you don't trust yourself, graph it and verify it. Okay? Would you like to try? Would you like to try 42? See what that looks like. G of x is x over 1 plus x squared. What do I have to do for my first derivative? Quotient rule. Everyone's favorite, right? over what? Let's simplify that just a little. That's going to be, if I wrote it up here, 1 plus x squared minus 2x squared. What's that? 1 minus x squared over 1 plus x squared squared. Okay. Unfortunately, what do we have to do? We have to do again that second derivative. That was first derivative. Now let's take the derivative again. I've got x squared denominator. What's the derivative of the numerator? Yes. Minus the numerator times the derivative of the denominator. Ouch. Let's change it, isn't it? 2 1 plus x squared to the first times the derivative of the numerator. Okay. Over 1 plus x squared to the fifth. Not pretty. Oh yeah, oh yeah.
You have 1 plus x squared on the top, and you have 1 plus x squared times 1 plus x squared. You cancel those out.
Up here you mean?
No, up on one.
Well, remember, if I did that, it would be, but it would be 1 over 1 plus x squared,
Up on that back side.
and then you would still have the minus 2. So we would have 2 quotient roots to do. So it's sometimes it's a toss-up, but I like that you look for that. It's good. Can we do much simplifying then? Ooh, yeah. Let's see. If I brought it up here, that is 1 plus, if I distributed this out, 1 plus 2x squared plus x to the 4th. Is that good? Times negative 2x. And then I've got, oh, look at this. I see something. I see 2 times 2x is 4x. So that's going to be minus 4x. I see 1 minus x squared times 1 plus x squared is actually 1 minus x to the 4th. All over 1 plus x squared to the 4th. Okay? If I do a little arithmetic on this, if I distribute my negative 2x minus 4x to the 3rd minus 2x to the 5th, okay, minus 4x plus 4x to the 5th, all over 1 plus x squared to the 4th. Did anything cancel? Did you see something not good? Anything? If I sort of simplify a little bit, that would be negative 2x, no, the 2x to the 5th. Let me erase it. 2x to the 5th. Minus 4x to the 3rd minus 6x over 1 plus x squared. If I set this to 0, I only have to set the numerator to 0. Can I factor that? I can factor out what to begin with. I can factor out a 2 and an x, right? 2x would be x to the 4th minus 2x squared minus 3. equals 0. 2x, and I can factor that, I guess. I hope so. X squared, 3, 1. Which one would be negative? Positive 1, negative 3. This one, if I set it to 0, has no real solutions, does it? See that? If I set x squared plus 1 equals 0, it would be I, wouldn't it? Or negative I. This one, though, 2x equals 0, x equals 0. If I set x squared minus 3 to 0, x squared would be 3, and x would be plus or minus root 3. Boy, that was a long way to go, wasn't it? So my intervals are not pretty. My intervals would be what? Negative infinity to negative root 3. From negative root 3 to 0. Would you agree? 0 to root 3. And root 3 to infinity. This is the reason you should always try to pick problems that you're not going to regret working on the board, right? I picked this one out because I thought it looked good and it turned out to be sort of ugly. Okay? What I would have to do is test into my second derivative. Wow. Which was that, right? Yeah. Could it be negative 2 in this one? Could it be negative 2? Like, isn't that like 1.7 something? So I would say g double prime of negative 2. What would that be? Wow. Ooh. Okay, let's be clever. Let's be clever. Yeah, you have to put that. What if I said this, and I don't want to make you jump off the cliff or anything, but what you would do is you would just test a number from each of these and see if it was concave up or down, and that's all they would know, right? Once you start, but that would take us a long time to actually finish that, wouldn't it? Okay? And I would not make you suffer through that on a test. That's too long. But did you see the process was the same? We found the second derivative, we set it to 0, and then, okay? It would be interesting to know that, but
Negative 31,
so this was negative?
that was negative.
Okay, so that'll be concave down. If I put negative 1, which would be in this interval, is it positive? Concave up. If I put 1 in, concave down, and put 2 in, concave up. All we worried about, we didn't care what the number was, we cared about the sign, didn't we? And if you didn't trust this, why don't we just, that's easy to graph. If I graphed, I've written over my original, it's x over 1 plus x squared, right? X divided by parentheses 1 plus x squared. That took it all, didn't it? That's good. If I leave it on a standard window, zoom 6, I'm going to zoom in once. Zoom in. Look at that. Okay. So what did we say? Up to negative 1.7, it's concave down. Up to negative 1.7, it was concave down, then it switches to up. Right? And where does it switch again? At 0? That looks right, doesn't it? At 0, it switched to concave down again. Right? From up to down. And then it switched back at 1.7. I would have to go out further than that. I would have to say maybe negative 10 to 10. Would that be a better picture? Much better. Okay. Good.
Did you see where Scott Kelly wanted the instantaneous rate of change? Did you see that on the
I
show?
didn't do that. I heard that he came back.
Yeah, well, they had debris flying, and they had to get battened down and everything, and they were trying to do the math to figure out.
That's so good. See, that's real. What I thought was good that's not as real, but I thought was great.
But
The
he
Martian.
didn't figure the problem out.
You did figure you did? Did
Yeah,
you see The
I did.
Martian, where math and science was so important that it saved his life? Love that.
He probably
The Martian with Matt Damon.
Oh, yeah,
Love it.
right.
Oh.
That was a
I was so impressed. I thought, yes. If he didn't know science and he didn't know math, he would have thought it's great.
The smartest partner from that thing.
I'll recommend that if you haven't seen it. I thought it was great. Let's see. So you see how they could get sort of hairy there, but we got a good result. Turn to 280. Let's see. On 280, look at what the question is. Find the inflection points, if any, of each function. Why don't we try 52, which will be much prettier than what we just finished, right? 52 says g of x is 2x cubed minus 3x squared plus 18x minus 8. The question is find the inflection points, if any. What's the first derivative? Good. What's the second derivative? Is that right? Okay. 12x minus 6. If I set that to 0, 12x equals 6. So what is x? So what we're saying is, if we did this correctly, negative infinity to 1/2 and 1/2 to infinity are my intervals, right? I would have to test, this would be so easy, next to the last one. G double prime of 0, is that okay? And test G double prime of 1. Negative 6, positive 6. So this is concave down. This is concave up. Since it switched from down to up, 1/2 is the inflection point. Okay? So we would say inflection point at 1/2 comma, whatever we get from our original function. I'll plug in 1/2. You want to race? You want to see if you can get on your calculator faster than I can get it on the board? Let's see. Is it a half? Is it also a half? Who won? Did you win?
I was looking. I had to figure out
Did I do it right?
Yeah.
Don't you love arithmetic by hand? Almost as good sometimes. Right? You don't like that. But I got a good word out of it. But do you agree that's where it should be? You want to see if that looks correct? If we graph it, call it out to 2x cubed
Minus 3x squared plus 18x.
minus
3x squared
and then
plus 18x
plus 18x
minus
8. If I go back to Zoom 6, can I see it? Not enough of it. Okay? I'm going to zoom out. Zoom 3, what we're saying is, if I went to my table and I put in 1/2, it should be at 1/2 where it changes. But if I put in 3 if I put in -3, look at that. So I need to set my window maybe, what if I said -10 to 10 for x? But let's go way up and down. What if I said -100 to 100? That would be concave down, concave up. Let's switch to good. What's interesting there is that there's not really a max or min to here, is there? But it did change concavity. See, it's curved down over here, but then it starts to curve up. And that's what we need to know. All right. How about, I have marked, actually, so this one must be a good one. Before we can do 66, I need to define the second derivative test. Do you remember what the first derivative test was from our last test? Let me remind you. Do you remember if we would have the intervals of the critical numbers, split our x-axis into intervals? We would have, the interval would either increase or decrease, wouldn't it? We said if it increased then decreased, what did you have? Max. If it decreased then increased, you had a min, correct? That was the first derivative test. Here is the second derivative test. Okay. Let C be a critical number on f of x, just like we found. Zeros of the first derivative. And let f prime and f double prime exist. This is where it gets great. If f double prime of that critical number is negative, that means it's on a concave down interval. What would it be? It would be a max, wouldn't it, at the top of that interval. If f double prime of that critical number is positive, that means it's concave up on that interval. That would be the bottom of it. It would be a relative minimum. And if f double prime of C is 0, the test is inconclusive. Let me tell you why this is going to be really nice. What we used to have, if we had a function, if we wanted to find out if something was a relative max or a min, then we have to use that first derivative test. If it was increasing and decreasing, it was a max. If it was decreasing and increasing, it was a min. Now, I'm just going to test that point from the first derivative inside the second one and talk about the concavity. If that point is on a concave down interval, that's a max. It would be the top of that interval. If I test this critical number into the second derivative, and it's positive, concave up, minimum. You see how that's going to be nice? I don't have to do all that increasing and decreasing stuff. I can just plug it right into the second derivative and say, hey, what's the concavity? Maximum or minimum? Nice. Like it. So let's do that for 66. Another one that's not too bad. 66 says f of x equals 2x cubed plus 3x squared minus 12x minus 4. Look what the instructions said. Find a relative extrema, which are relative max or min points of each function, and use the second derivative test if applicable. Well, let's find their critical numbers. What is the first derivative? Remember, if I want to find the critical numbers for max and min, I set this one to 0, don't I? First derivative to 0 to find the critical numbers for max and min. Can you factor that for me? What comes out first? Yes. I agree with 2 and 1. Which one will be positive? Yes. So what are my 2 critical numbers? Negative 2 and 1 are my critical numbers. Zeros are the first derivative. Okay? Now the question is, do those lead to a max or a min for that function? Well, to make it easy, let's find the second derivative in that and use that second derivative test. What is the second derivative? Very easy. Yes. All right. So now let's test them. What is f double prime of negative 2? Yeah. It's negative 18, so that means it's right. It's an interval that's concave down. So if it's an interval of concave down, that'll be the top of it. It'll be a max. Relative max at negative 2 what? Where do I put it to get the point? The original function. You want all of us do it by hand this time? Negative 8 times 2 is negative 16. What's that? 4 times 3 is plus 12. Plus 24. Minus 4. 36 minus 20 is what? Is that right? 36 minus 20 is 16. Relative max, negative 216. Not bad, right? Tell me f double prime of 1. I bet we can all do that. Right now here. 5, is that negative 11? Or no, it's 11. What? Hold on. Negative 11? Oh, wait a minute. No. I'm plugging 1 into my second derivative. Yeah. It's going to be positive 18. F double prime is yeah. Positive 18, concave up. Concave up means relative to mean. I was jumping the gun on the original function. Now put 1 in here, and you said that was negative 11, right? Correct? You buy that? You think those are my relative maximum? If I graph it, if you don't mind calling it out to me one more time, 2x cubed plus 3x squared. It didn't do my cube, did it? That's in the box. 3x squared minus 12x minus 4. Now looking at what we found, I'm going to have to go up to 16 and down to negative 11. So I guess I need to say, for my window, I will say negative 20 to 20 would be a good window. Cover those lines. Does that look like negative 216 and negative and 1 negative 11? I think it does. Negative 2 and up 16, positive 1 and down 11. Backs it right up, doesn't it? Some of you on the last test admitted to me. I said, how did you find the maximum? I graphed it and I used the calculator. Meaning they used no calculator. It's very like a knife in my stomach.
Get back to the notes.
What's that?
When you get back to the notes.
Sure. That calculators did to back it up. This is what I'm looking for. They said use the second derivative test, and that's what we did. So, and it's not that hard, is it? Find the first and second derivative, find the zeros of f prime from the critical numbers, then test them in the second derivative to see if it's negative or positive.
these kind of stuff, the ones you do.
Oh, that was well, see, that made a good point, though. There are some ugly problems.
So the critical numbers, you go back to the first derivative, the zero,
Zeros are the first derivative.
and then concave up and concave down.
Plug those results, plug those critical numbers into your second derivative to see if it's concave down or up. Concave down would be a max, concave up would be a minimum. That sort of reverses your thinking, doesn't it? Remember how we would
Yes,
say,
because, and then the relative max is backed up into the original, right? Mhm.
well,
That's
then,
what's confusing.
once you figure out what they are, you find the order here is by putting these critical numbers back in the original. Yeah. That's where we got the negative 216 and 111. That's good. Why don't we try 72? See how we do on that. 72 says, it looks innocent, but really, g of x equals x squared plus 2 over x. How could I write that? I like that. Because we're going to be taking derivatives, so I'm going to write it like that. Alright. So what is g prime of x? Good. That's what I set to 0 to get my critical numbers. So if I say 2x equals 2x to the negative 2, what does that mean? 2x equals 2 over x squared. If I clear the fraction, 2x cubed equals 2, so x cubed equals 1. My own solution to that would be 1. The other two would be imaginary. Right? Say that again. It could be, yeah, we would have to say if we said if the first derivative was undefined, it could be. Right? It could change. Right? So we might need to test 0 to see 0 might be or might not be. What I'm thinking of is if our original function was undefined, it would not be. Remember, didn't it say if the derivative is undefined but the original function is defined? So I'm thinking if 0 made the original undefined, I don't think you have to worry about it. Look back at our notes. I think that was an so we've got one critical number. What is my second derivative? 2 plus 4 x to the negative 3. Right? Which means what? 2 plus 4 over x cubed. Right? So my two intervals would be negative infinity to 1 and 1 to infinity. And actually, like we said, 0 would not be a possible value, so I guess we would have to say something like 0 to 1, because that would be sort of an asymptote to the original value. So I guess I would want to think of it more like that for a second. 0 to 1. And then we could say negative infinity to 0, just so we didn't have that 0 in the midst of the number. Okay? So, what we wanted to do, though, we weren't really concerned about the intervals. We wanted to use the second derivative test. So if I say second derivative at 1, what do you get? If I put 1 in here, I get positive 600. That's concave up. So what will it be? Concave up would be minimum at 1. What if I put 1 in my original? 1 plus, would it be 1 plus 2? 3? You want to test it? x squared plus 2 over x. I graph it. X squared plus 2 divided by x. 2, 6. You see this one never has a maximum, that piece of it, so that didn't really matter, but when infinity to 0. But look at that, we did it, didn't we? It's at 1, 2. That's great. What do you think? Don't you love being able to back that up? On that next test, if I say use second derivative test, they'll be saying, well, I look at the calculator like that. That's nice as a backup, but don't be saying that's how you do the whole problem. Right? What are we studying here? Yeah. That's good. You should always back up this. Okay, I think we have time for one more problem. I'm going to hand back to this. Let's see. Why don't we try this one? 90. 90 says, the altitude and feet of the rocket 2 seconds into flight is given by S equals negative 2t plus 54 t squared plus 4 over t plus 6. That's for t greater than 0. Find the point of inflection and interpret your result. What's the maximum velocity attained by the rocket? Okay. Remember, if this is a distance function, the first derivative is the velocity function. Tell me what the first derivative is. Good. Go ahead, they say find the inflection point, so I'm going to find the second derivative. Well, I'll set that to 0. Negative 6t equals negative 1 over 8. Is that what you do? All right, so at 18 seconds, there's an inflection point. Let's think about this a second. If I had two, let's see. So the inflection point is when t is 18. They said, what is the velocity when we could plug 18 back into the original to find out what the order here on the original is, but they said, what's the velocity? Let them read that question again. It says, what's the maximum velocity attained by the rocket? Well, this is what I want you to see about this. Would you agree that that velocity function is a downward track? Right? Well, this, remember how we would find the critical numbers, the first derivative to get the maximum? Well, if you take the derivative of the derivative, that gives me the maximum for the first derivative. The second derivative gives me the maximum for that. If this were my original function, wouldn't you say this would be the critical number? That's what they're getting at. So the maximum velocity is going to be the maximum of this. That's going to be a max, isn't it? Happens right there. Plug it into your velocity function. So if I said S prime of 18, tell me what you get. I'm not going to do that in my way. Let's do it on a calculator. Oh, great. And that's going to be the units we're in, feet per second. Would that be the velocity? Per second. Okay. This is what's interesting about it. Remember, this was the inflection point. Okay. That's the inflection point of the original distance curve. But it turned out to be the first derivative of the derivative. So that gave you the max velocity. This is my velocity. Okay. And that's what you're doing. Nice. So, the ones I want you to try from this set, very selective ones, on page 279, 25, and 59, go the other eye. Some of them might be ugly, and I apologize in advance if they are. 61 through 67 eye, 71, and then 89 through 95 gives you 3 word problems to practice. I might do one more word problem next time before we go on in this section, but you let me know how those go. I want to spend the rest of the time letting you look at your test and ask questions if you have them. Make sure you understand what you did. If you see these on file. I would like to do that, but I want you to ask questions. I'll work out and see what I'm doing. Most people, I think, will understand what happened on the front page. Some of you just made a sign error with your revenue minus cost. I try not to pick off too much for that. Of course, the problems came in number 5, didn't they? Most of you got number 4. And you took the derivative of p. Look at what I wrote on number 4. You missed it. The derivative is 4 power squared dr dt. And you plug in what you was given, and you found that was number 4. Problem came in on 5a and b. You were given x squared, y squared to the 16. You had to use product rule, and some of you just completely blanked that out. Right? You have to say first times derivative of second plus derivative of first times original second equals 0. That's product rule. Anytime I took a y derivative, I tacked on dy dx. Right? Some of you told me 2x, 2y, and I was very sad. I was very sad. But if I solve for dy dx, I'm going to subtract this term from both sides. So I'll have 2x squared y dy dx equals negative 2xy squared. When I divide out that coefficient, you get a negative y over x. That's dy dx. And some of you freaked out even further on part B when I gave you square root of x, which is this, minus square root of y, which is this, equals 1. Same type thing. 1/2 x to the negative half minus 1/2 y to the negative half dy dx equals 0. If if I move this x term to the other side, I get negative 1/2 y to the negative half dy dx equals negative 1/2 x dx. When I divide, what happens to the negative 1/2? They cancel. If I want to make these to the positive 1/2, I swap them. This will go up and that will go down. So it is dy dx equals y to the 1/2 over x to the 1/2, which is square root of y over square root of x. If you plug in the xy order here I gave you, 25, 16, that was square root of 16 over square root of 25. So the slope you needed to use, the slope of the tangent was 4/5. And all of you could write that equation once you got that. And I gave you half of it. You even had a wrong slope if you wrote the equation. Okay? And then you would write y minus y1 equals n times x minus x1 using that slope. Everything else, most of you got, and I think you'll understand the mistakes. Those were the two tricky ones. This one especially. But if you understand what you did, hand it back to me. If you need any further guidance, stick around. We'll continue on Wednesday, and then we'll have spring break.
You're not loading this up on Wednesdays, are you?
Loading you up, no. We're just going to do about 3 sections Wednesday. No, I'm just joking.
I want to be home.
But yeah, just normal.
What is normal?
How was that? Thanks. Good job. I was happy. That might have been the best one in the whole time. Have a good one. Feeling good about your test, Thursday? Yeah. We'll finish the review tomorrow. Write it down.
I did that just wrong.
Did you understand most of the mistakes?
Yes, and it's just from being sick and not